We are going to start now lecture 2, in which we start to look a bit more in depth to what we want to do. There will be still another level in which we go to the real details, but in this next 50 minutes or less, I'm going to introduce the model of the, well, I already introduced the model of the HALD spheres, but I'm going to go a bit more into the detail. So, like we did in the previous lecture, here is an outline of what we want to do. First, we want to understand what we are talking about. We want to define this HALD sphere so that we have a model that then we can do things with it. We want always to plan what kind of thing you want to learn from the model. You have to plan the simulation. Before you start coding anything, you need to know what you want your simulation for. Then once you know what you want it for, you can design the algorithm. And again, in computer programming, my experience is most of the time should be done in that step. In practice, many times, and this is my case too, although I try to change it, many times you want to code as soon as you can, and you kind of plan and code at the same time. The best results I always have got when you do a lot of the thinking first, and then you just write the code. So much more time goes into the planning and writing with your hands, and less goes into the typing. And then once we have the algorithm, we'll take a few minutes to talk about how to implement it in whatever language you used to do or in the ones I'll suggest. So again, the real question is not what the spheres are, but what do they do or how do they behave? The kind of what they are is always more philosophical question than scientific. So we want to know everything about the behavior of these spheres. So they are what the name says. They are spheres, and as such, they will be characterized by a diameter, by a length. Okay? We'll call that sigma. These spheres, as we said in the previous lecture, they don't attract each other, they don't repel each other, they just move around until they find each other, and then they rebound like two billiard balls, good rebound. And every time this happens, energy is conserved, and obviously linear momentum is always conserved too. So we'll get, in general, in our system, there will be two balls I and J. They will be moving around until they collide, and when they collide, it will be easy to track. We will have to be able to track what exactly the velocities do. Before the collision, they were constant. After the collision, physics have to tell us what happens to them. So if they are going at constant velocity, then the equations of the movement are very simple, as you all hopefully remember from your kinematics course. The position is at every time is the initial position plus the velocity times the time. This is true for the two of them. So we can always track the distance between them because we know the positions between them. So if you get the modulus of the vector, that is the difference of these two, this is the distance between them, and it will be a function of time. So here in this step, the only thing I did is I plugged these two things here and I expanded it. Now you have a second order equation, just algebraic equation that you solve with a very simple formula that you learn in your primary school, and you get the expected time to collision. This, with some variables to make things easier to write, this might be a real number or might not, because the two balls, nobody says they have to collide at some point. They might be going in totally opposite directions and they will not collide. So in that case, you will get a Tij that doesn't make sense. But if they do collide, you'll find the Tij. Okay, so far, this is quite simple. Now we arrive at the moment of collision and what happens there. So as I said, linear momentum will be conserved, like in any collision, and energy will be conserved, like in any elastic collision. Energy, in this case, is only kinetic energy, because we've said that our model is so simple that there are no forces, which means there are no potentials. There is no potential energy. So the energy is equal to the kinetic energy that you, again, remember from school, that is just 1/2 of the mass times the square of the speed. If you use these two equations and you think of what two balls should do once, in which direction they would rebound, you can arrive to this equation that says that the velocity of one will be the opposite of the velocity of the other, the change in velocity, sorry. The change of velocity in one of them will be equal to the change of velocity of the other, and it will be given by this simple equation, where the Bij is one of those products of velocities and positions that we saw before. So now we can track these balls forever. Okay? We know now we could compute again when they are going to collide again. If these were just two balls in the universe, they would collide at most once. They would rebound. Each one would be on its way somewhere. But in our simulation, obviously, we have many more. So one thing we have to do is, and this will be true for all the models we use, we have to put there some boundary conditions. We have to limit the problem we have to some particular amount of space. So there are several ways to do this. For the hard spheres, we could put them inside a box, like in an ideal gas. So we would track the movement inside the box, and when they reach the wall, they just rebound again with the basic equations of dynamics. This can be done, but it's simpler and better for convergence of the simulations to use what is called periodic boundary conditions. So instead of having real walls, what we have is a system that is inside the box. Our system will always be inside the box, in some region of space. And then periodic boundary conditions means that when one ball reaches the wall, it will come again to the box through the opposite side. Okay? So you can see here that this ball is going that way. So if it goes through here, it will come back through here like this one is doing. So if you think of two of the balls now, because you have periodic boundary conditions, it doesn't mean that if these two will never, if these two are not set to collide, there might still be a collision, because they might collide when one of them comes back to the box. Okay, this is an important point, because for the code, we'll have to take this into account. Again, this ball might collide with any of the copies. Everything goes on only in this box, in the central one. But just because this one goes this way and that one goes that way, it doesn't mean they don't collide. They will collide because this one, which is a copy of that one, when it goes through the wall, will come back through here. And they will collide here. Actually, the example was drawn so that they would collide.
So the red one is also replicated?
Yes, but every time you think, you can, one of them, you can just.
So if they collide now,
yeah,
the red and the blue one, so the collision will be everywhere in all the boxes around?
No, I mean, well, yes. I mean, at the point they collide in all the boxes, yes.
Okay.
But for tracking purposes, you only need to compute where are the copies of one of them. The other one, it doesn't matter. I mean, wherever they are, they collide in all the places. So now we are able to track what happens at every time at every point in the evolution of time. We can start following every couple of spheres, compute when they are going to collide, evolve every sphere for that time, and then compute what is the change in velocities at that time for those two. You have many spheres in general. Okay? There will be many spheres in our material, so you have to find which one is the next collision. What you have to do is to take every possible pair of spheres, compute when every possible collision is going to take place, and then pick the smallest of these times and evolve all the balls during that time. How do you evolve them? You know that the position is the initial position plus time times velocity. Yes?
Is there something clever you can do in order, that after a collision you don't have to calculate everything, maybe just calculate something local?
Yes, there are. I mean, if this was a real code, you would do a lot of tricks like this. So one thing that we will do is, after a collision, you don't need to compute. So how does it work? Some of the ones that were not, I mean, if particle K and L were not bound to collide, after this collision of I and J, they will not collide anyway. So you don't have to recompute again the time of K and L, because they might collide with I and J, but this you are doing while you compute the pair IK, IL, JK. Yeah. I mean, these things are a bit technical. You need to think. There's no way around it. You need to sit down, think about them, and learn to program this. Because if you program without the thinking, you will write much longer code, much slower code, much worse code. There are always tricks to save time. There is always a trade-off between the implementation of the trick and the time you want to serve. So, for example, I usually, and also there is some drive to, when you get some routines from someone else, you want to optimize them, you want to do them your way. I never optimize anything unless I can make it twice as fast, or twice as clean, so twice as short, or somehow I can comment. You have to make a significant change. There is no point in trying to think how to get a second from every line of the code. Also, there is this rule that applies in everything of the 80-20. So 80% of the time of your code will be, 20% of the lines will be responsible for 80% of the time that your code runs. So work only on those lines. But if you want tricks, there are tricks for everything. And if the trick is clever, it's certainly worth. If the trick means multiplying by 10 the amount of lines and getting a 10% increase in time, it's probably not worth. Okay, so now we know everything about our systems. For every instant in time, we can know where each ball is and what is the speed of the ball. And this characterizes completely the system. There is no unknowns here. We can track it forever. What do we want to do with that? I mean, that's very good, but now what? So what we want to do is, as they did, we pretend that this is again 1957, we want to know if a phase transition can arise in this very simple system or not. Are there regimes of this very simple system that are very different to each other? So, well, now we know that yes, the answer is yes, but the answer was not so obvious. I mean, there had been some studies with another method that is called Monte Carlo that were recent, so they were hinting at this. But molecular dynamics helped to prove this. Again, it all depends on how deep you want to go. There are still today, there are papers of hard spheres model phase transition appearing in which whatever the balls are different size or there is something new to learn about it. What we want to know is if our system shows a phase transition. In order to see that, we want to know the equation of state of the system. The equation of state of the system gives us the state of the variables that represent the system when the system is in equilibrium. Typically, for this kind of thing, like for the ideal gas, it's a relationship between the pressure, the volume, and the temperature. Okay? Now, there is temperature, there is obviously volume in this system because the box has some size. There is pressure of the system because if the box had walls, if the box had walls, the balls would be colliding with the walls. And there is temperature in the system because temperature is just the kinetic energy of the molecules, of the balls. Okay? Now, what is the relationship between them? So we want to plot that relationship, and you probably cannot see it because I took the graph from the paper and they wrote in very small letters, but this is PV over KT, this axis, and this is the volume over some renormalization constant. So we want to basically know what is the value of PV over KT. Okay? So for an ideal gas, this is 1. Right? You remember that. For a liquid or a solid, the model of the ideal gas is not good anymore. The ideal gas, if you remember from your thermodynamics, the equation of the ideal gas comes with the assumption that the balls are infinitely small. If we are in a solid, the balls are very close. Most of the solid is balls. They are not small. They are huge. Okay? So then you need to add something to this equation. This, I haven't computed it myself, but I think it's not very difficult, so I'll give you homework to do it. You can look at, it's in books, whatever, you can get inspiration for those books. Try to think of it without looking at the books and then looking at them. Make sure you understand it. Okay? So what it says is that the PV over KT curve is 1 plus something that depends on constants, like the radius of the balls, how many I have, what is the average speed of them, which is constant because the average speed is linked to the kinetic energy, which is linked to the energy, which is constant. And then it's a term, it's a sum, it's divided by the time of the simulation, but what is important here is the sum of changes of velocity of all the collisions. So you can relate the pressure in the system to how often and how big are the changes in the velocities once the balls collide. Okay? If they collide very often and very strongly, the pressure is higher. If they collide very seldomly and very weakly, the pressure is low. And how do we know if there is a phase transition? If there is a phase transition, there has to be a region where you can get both of the phases. Okay? So we are going to do simulations for different temperatures and volumes. We are going to find the pressure, and then we are going to plot these lines. Here you see many lines because, as I said, there was some previous simulations with Monte Carlo, etc. The ones we want to get are these two. One is here, and one is here. So there are points of the space of phases where the system can be in two different phases. One is like a solid, this one, and one is like a liquid. Okay? So we need to run many simulations to get points for these curves and see if we get one continuous curve, so only one phase, or two curves. We should get two like they did.
Can you show again? Where do you see the first one?
Because there are two curves of PV over KT, this one and this one. Where, I will fix this point and I will compute PV over KT. And I might get this point or this point depending on the initial conditions of my spheres. This is why I need to do several random simulations to make sure if I do whatever, 100, I don't know, I haven't thought of how many you have to do, but if you do 16, whether the 16 end up in the same place or 5 of them in one place and 11 in the other. Okay? So every time you do a simulation, you get a point. When you get many points, you might get only one curve or only two. Again, the random initial conditions are very important because are the ones that are going to allow you to explore the different phases. We will also plot this kind of graphs to see not only in this way that there is a phase transition, but that there is something very different in the system. So these systems, for the same volume, they show two very different behaviors. One, the one here, is like a solid. The balls are, so there is a ball that is whatever this size, and another one this size, and they just collide with each other, and they move, they vibrate inside a little bit. What you see here, these lines, were obtained in 1957 with some clever device. It measures the center of the ball. The balls are obviously have to be very big. If they were very small, this would be not a solid, it would be a gas. But this is the trajectory of the center of the ball. So you see that no ball leaves its average middle point, is a solid. Here they do pass each other, is a liquid. And again, temperature and volume will be the same, and pressure. No, one of them cannot be. We'll see about it. So how are we going to implement this, or what do we have to think about it? Well, a trivial thing you always have to do when you write a code, and many mistakes can be done already at this stage, is to pick your units. Like in DFT codes, you usually work in atomic units. You try to make the equations as simple as you can. In this case, we can set the side of the cube to be just whatever length we want, so we'll set it to be 1. This is very important. Well, this is very practical, because then periodic boundary conditions are very easy to implement, because if a number gives you a position 36.82, if you want to bring it back to the box, it's just 0.82, because the box is length 1. Doesn't matter if you don't understand this, it will come back again. But we can set the length to be 1, and this will determine, we influence what is the diameter of the balls, okay? Because there is a length scale, which is the diameter of the balls. There is a mass scale, which is the mass of the balls, and we can set it to 1. And there is no energy scale, because the energy is constant, and if you look at the hard spheres as a potential, it's just an infinite well. So there is no, it's not finite, there is no well depth, it's infinite. So there is no scale, so we set up KT to be 1. Okay, so when we write our program, we'll take into account all that. We'll use the formula, we'll set up the formulas as appropriate. And now, next thing is what are we giving to the program, and what do we want from the program? So what are we giving to the program? We'll need to give how many balls you have in that cube of 1 unit volume. You will have to give to the program how packed is the system. So what is the, so there are several ways to do this. You could set the diameter of the ball, and this would fix how packed the system is. But it's more convenient to do it in this way. Again, we'll go back to it, but it's basically the volume of the system divided by the volume that the spheres would occupy in the closest possible packed system. Again, this is technical, but at least it's well defined. So when you think about it, you'll find out what I mean. And the only other input you need to give is the time. But the time is, again, an abstract concept. It will be given by how many collisions you want to simulate. So you start the simulation and you want to do 1,000 collisions, 10,000 collisions, 100,000 collisions. You don't know. You need to do as many collisions as to get equilibrium. And again, you want to compute PV over KT. You can compute this with an average of 100, 1,000, 10,000. At some point, it doesn't matter. I mean, you have to get convergence. If you do 1,000,000 steps, it cannot change from 1,000,000 to 2,000,000. So you want to do as many steps as they guarantee that nothing new is happening in the system. Every ball now is basically randomized, but not too much, because every time you need a collision, it's more time on computer. So you'll get a feel for how many you need. But anyway, at this stage, it's just a parameter of the code, an input variable.
What is a small n?
Sorry? What is a small n? Sorry. So, okay, this is also a technicality. How many spheres are we going to put? So we are going to start always, for simplicity, from a face-centered cubic lattice. Okay? So in a face-centered cubic lattice, is there anyone that doesn't know what a face-centered cubic lattice is?
I'm not sure. Is it just a cubic lattice where they're all centered around the center of a unit cell?
So in a cubic lattice, if you have a cube, you have spheres in every corner of the cube, and you have 6 spheres in the center of every face. And it's the closest possible packing you can do for spheres. So is whatever. The typical example is a pile of oranges in the market is piled in this structure. So we want that, but for that, to build cubes out of it, we cannot do it with 3 spheres or 33. They don't form a nice cubic shape, only if they are of the form 4, 32, 91, or whatever, 4 times an integer to the cube, they will work. 108, sorry. 108, 512. There are not many, but you don't care that much either. You have to have enough, again, to randomize your system. If you have too little, you don't really have a material that is melting or whatever. You have a solid that is vibrating only in one direction or whatever, if you only have 2 bolts. So the more similar it is to a real system, but the more it costs computational. So again, you do enough to get convergence. When you put more balls and nothing changes in your curves, you reached the point you wanted. Now, what do we want to get? Of everything I say, you should think about, and if you think we should get other input and things are easier, etc., all this, will add points to you if you are correct. Don't do just what I say, because this is my way to look at it. There are many ways to program and to do algorithms. I think this is the simplest, and certainly I look at them, but there is always room for improvements. So what output do I think we should get? Well, we should get output enough to track what happened in the system at any time. And this is basically where everybody was, where every ball was, and what was the velocity of every ball. So we'll write the initial velocities, and we always write the input, and then we'll give information for every collision that will contain if it is the first collision, the second, the third, whatever, how much time has passed, what is the average linear momentum per sphere and the average energy per sphere, who collided, and how did the velocity change. Now, why do I write all this? Well, this is for tracking purposes, and this too. I want to know a way to, for every time, know where everybody was. For that, I don't need the average linear momentum, and I don't need the average energy. But I still compute them. This is very important every time you code. You not only need to compute the things you want to find out, you need to compute things that reassure you that you are doing the right thing. So I know that linear momentum is conserved, and I know the energy is conserved. But this is a numerical program. There is always round of errors. There are things that can go wrong. Maybe I have a bug. So I always have to make sure I record information for testing, not only for outputting, but for testing. So these are typical things you record. And every x steps, you make sure the momentum is okay, and if not, the program stops and tells you the energy has changed too much, something's wrong. And the change in velocity is because this is the variable I need for that equation of state I show you, for the PV over KT. Okay, so now we know the input and we know the output. What is a possible way to go from input to output? Well, obviously you will have to read the input, and you have to learn how your language reads input, but usually it's a very simple read statement. So you will get the variables, you will write a little file with the 3 input variables, and the code will be able to read these 3 input variables. Then, again, this you don't need to do, and if we were perfect programmers, we wouldn't do it, but you need to check that that input makes sense. Maybe someone put a value of those number of spheres that is not 108, but 1080. That's not good, so we stop the program. Or maybe someone gave a volume that is even smaller than the one that comes from the closest possible packaging. This will not stop the program per se. The program will, if you don't do anything, it will run and will give numbers. Then you will have a problem when you don't understand the numbers. So it's better to always try to catch possible errors before. Then we'll find what are the diameters of our spheres, because we know that the box is length 1, and we know how packed they are. But in many of the equations, we need the diameter. So you can see, again, you should go over all these things and make sure you understand these equations. Some of them might have a mistake, for example. So always check these things and make sure you understand them. You don't need to know any deep physics or mathematics for these things. Okay, so now we know how many balls we have. We know how many steps we want to do. We know everything about our system. We just need to generate the initial conditions. Okay, and these initial conditions have to be random. I mean, if we are going to do simulations, if they were not random, every time I do a simulation, I would get the same random answer. Okay, so there are several ways to go about it. You could put the randomness in the positions and the velocities, or only the positions, or only the velocities. One that works efficiently is to put the balls always in the same place, but then to give them random velocities. And this is done also in molecular dynamics in more advanced methods. You just, in a sense, melt the system. You put it in an FCC, every ball exactly in the FCC positions, but then the velocities of the ball are random. So very soon you get a lot of noise in the system, and the correlation between the distances of balls disappears. Okay, it becomes really random. For this, you have to think how to generate random velocities. Again, all these things, when you sit down and you think about it, it's always much more complicated than you think. You need to come with some idea so that the velocities, every ball is released in a random direction. Think of what random means and operate accordingly. If you, by chance, give something that is not random, you might get wrong results because your system is not accessing all possible energetic configurations, but some that come from your particular choice. Then, again, things converge more slowly, things take more time, things sometimes give the wrong answer. So at this point, we know what the positions and velocities are, the initial ones, so we write, yes? So every time you run a simulation, you randomly generate the velocities. You need to run many simulations to compute anything of use of this system. With one simulation, you don't learn anything. Or, you learn if your code looks correct. It's the only thing. All this is statistical mechanics. It's going to be based on many trials. once you have the positions and velocities written, you have to start taking care of tracking all possible collisions, okay? Because the collisions have the most valuable information of the simulation. So you will create a table in your language, an array or whatever your language does, and for the table will have 2 indexes, and every pair of indexes will mean 2 balls, and you will compute when the collision time for each pair is expected, okay, as we said, because you want the minimum one. So if you have 3 balls, you need to know when ball 1 will hit ball 2, when ball 1 will hit ball 3, when ball 2 will hit ball 3. The minimum of the time of these times, you then allow in the next step the balls to evolve. Okay, you know their velocities and their positions, and nothing is going to happen in that time, so they just follow a uniform movement. After that time, they will be in different positions, and 2 of the balls will be touching each other. So this is a good moment to test that momentum and energy is conserved. And now you write to output how much time it passed, and what was the change in the velocities, and who were the balls colliding. Again, for recording all the information. Next step, you start again. You go to the table, and again you compute the time to collision for every pair. But again, as I said before, you don't really compute for every pair, because for many of them, nothing is going to change. Again, if ball 1 and 2 collide, and balls 7 and 8 were not meant to collide until 10,000 collisions from now, just because 1 and 2 collided, 9 and 8 are not going to collide sooner than they are going to collide sooner. You have to subtract the time that has passed, but nothing changes. Okay, so 9 and 10 go like this. Something happened there, down there. They keep going like they were. They might collide with 1 and 2 again, but that is a different entry in the table. What it means is updating the table is much cheaper than it seems. Doing a double loop over balls is very expensive. If you have 500 balls, you need to do like 10,000 computations. But because most of them will not change, you can just doing one subtraction is much cheaper than solving that second-degree equation. And now you look at how many collisions have I done. If I done the 10,000 I wanted, I stop the program. If not, next, 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 next. So as I thought of the program, I thought, again, and again, you can think of improvements if you want. I thought of doing the simulation totally independently from the analysis. So this Fortran code will run the system, will not compute pressure, volume, will not compute the equation of state. Will just run the system and write the information to output. Another code, which is more efficiently done in Python, will read that output and compute the things you want. So this simplifies the first task. Now, now we have a little plan to do our thing. How do we implement it? Again, if you have a language in which you are proficient, do that. Use that language, unless it's very slow for the simulation. If not, I recommend, and this is what I do for all my simulations. I write in Fortran the parts that are demanding computationally, like all these loops over balls, etc., so the whole evolution of the system, and I write in Python whatever tool I need to analyze the results. So for example, when we see density functional theory calculations, you run siesta, which is written in Fortran, and the output is many lines that contain the energy of the system, the position of the atoms, the value of the eigenvalues, etc. You don't want to open that file and go look for the energy you want to do it automatically. So you write another program in Python that goes to the file and looks for the line of the energy and prints it to you. Or if you like to print other things, like I do, you print tests that everything went well, that I don't have magnetic moments if I'm not supposed to have them, etc. Here is the same. So Fortran, as you can see, is a very old language. We are still using it. It's quite ugly, but we are still using it because it's very fast. Probably C and C++ are as fast, but there is a lot of libraries already written in Fortran. So people didn't switch to C or C++ because then you have to rewrite whatever routines you are using. And I remind you again, these are codes that are more than 100,000 lines. Just to port it from Fortran to C, again, depending on how good you are, but it will take months, even if you are very good. And then there are all the other not so good. So the good points are that it's very fast, and there is a lot of ancient code that is very fast too, and you can reuse, and that is easy to parallelize. You use some parallelization libraries that are quite simple to handle, and the matching between Fortran and these libraries is very good. Has been done for a long time, so it's very robust. It's basically very simple to parallelize Fortran. What is the negative points? On the other hand, also it's a very simple code to learn. You can learn it. It has very few keywords. You can learn it very fast. But it's very, because it has very simple syntax, and because it is very limited, to do things with it, you need usually to write a lot of code. While in other languages, if you want to split a word, there is a function to split a word in two. In Fortran, you have to write something. And everything takes many lines of code, because the Fortran is for formula translation. It was meant to do mathematics. Sums, subtraction, multiplication, a lot of them. So finding doing a string matching will take several lines of programming. So in the end, the codes are difficult or very difficult to maintain, because someone new comes, opens the code, and the code is boring, long, and is ugly. Still is efficient. Python is easy to maintain because the syntax is much simpler. It has many functions. So if you want, again, there are many things you can do with one line. To split a word in letters, to split a sentence in words, these are one lines in Python. So it's very good, for example, for text parsing, to find a string in an output file that looks for energy equals and spits out the value. While this takes boring Fortran many lines, takes Python few lines. There is also a lot of code for it because it's very popular, and there are many routines, so you can download routines and you can integrate them in your code. For example, you can plot graphs directly. You can ask your script of Python to go to your 10 siesta files, take the energy of each of them, and plot it versus whatever, the number of the simulation. And directly, the script will do it. It will plot for you a graph, because there are libraries that do this. So again, to repeat the same point, if you need many numerical calculations, use Fortran. If you need analysis that doesn't depend on speed, it's going to take anyway 10 seconds, and you don't care if it is 10 seconds or 1 minute, use Python. Never took a minute for me to analyze anything. It's always a few seconds. So this is how they look. They begin to show already part of what I say. These do the same. It's one of the simple ways to sort an array. an array. So already in Python you see it's much simpler. The simpler it is, it's always going to be easier to read for a human. So this is why, unless you need numerical speed, you always prefer something like this. And again, I said this before, you can choose other languages, but there is a reason why we still use Fortran, which is speed. In this graph, this is time of running, and this is a comparison, for example, with MATLAB, and MATLAB is up there, taking several orders of magnitude more than Python. One of the C's, this IL numerics is C#, which I don't know much about it, is as fast as Fortran. Now, graphs like this you can find of all colors, and this one was prepared probably by someone that wants to show that C# is fast. It depends on your problem, it depends on how good you were programming, etc., etc. It depends on many things, but it's in generally true if you see a difference of 100 times. Maybe it's not 100 and it's 50 or 150, but it is true that Fortran is faster than MATLAB by a difference that is important enough to use Fortran for this. I cannot spend 50 days instead of 1 day to compute my whatever, even if it was much easier to program in MATLAB. But again, C, C++, if you know this, go for it. Actually, as I said, for me it's better because then I have something to compare to. Maybe I discovered that C++ is much better. At some point, if it is 10 times better, maybe it's better to spend a year writing siesta in C++. And you can use Python and you can use Fortran in Windows, in Mac, or in Linux. If you don't have a very strong feeling about any of this, I recommend that you give a try to Ubuntu. Ubuntu is a Linux flavor that, as I said before, is very easy to use. And the way to use it is not to just erase your Windows from your laptop and put Ubuntu. Just install, learn a bit about how VirtualBox works, install it in your Windows, and your Windows laptop will always be a Windows laptop. But when you come to class or you work in your homework, you can open your Ubuntu machine, and if you put it in full screen mode, nobody knows that you have a Windows machine there. It looks like a Ubuntu, it works like a Ubuntu, it's even fast as Linux is almost, a native operating system. In the Siesta course we gave here last year, we used VirtualBoxes. Everybody ran the complicated examples in Ubuntu, and if we open the Ubuntu for them, they don't know that these machines were Windows. It takes a bit of time to get familiar to the two of them, but not a lot of time. So it all depends if. And I think it's a very good investment to learn about them. I find them very, VirtualBox is a very impressive product that you are able to simulate computers inside your computer is very good if you want to learn anything about computers, because as I said before, you can play with the operative system, whatever, it doesn't matter if you break it. You remove it and you create another one. And again, we use Linux because it's much easier to do tracking of jobs, sending jobs to run, and analyzing jobs. Everything is done with command lines. These take a little bit of time to learn, but then are way faster than doing anything with Windows, in which you click a file and you open and you look at it, etc. So basically, in the field of atomistic simulation of materials, the people I know, they all use Linux. The reason is this is much faster. I mean, it's much more efficient. And that's it for this lecture. You can see here what we accomplished today. And next time, we'll go a bit more deep even in the hard sphere simulations, and we'll start to look at how the programs should look like to start doing our simulations. So now, I think I've said most of what I wanted to say. Today we are not going to do anything in the computers. I would recommend you bring a laptop with Ubuntu, or not, but I recommend that you bring your laptop, because otherwise you have to come to here to work, or you have to have a way to port. I mean, it might be not very difficult to port files from the computer here to your computer to home, but if it's not a problem, bring a laptop with Ubuntu, and then everything is much easier. Questions? Sorry? Next week we'll start writing the code for the hard spheres. There will be homework for next week. It will be online in a few hours. The homework is basically install. No, not install. Is proof two statements that are there. One very easy and one not so easy. And run your first Python program and your first Fortran program. Again, I don't care how you run it. I want to see the output and the program. So you will send me, I'll give you instructions. You will send me the program and the output. There is, in every computer language, there is a program called Hello World. It's the most simple program, one of the simplest programs you can write. It's just for you to realize you can write something, make sure you know how to run it, and that does what you think it does, but it will be 3 lines. Also, you can Google Hello World. You will find people do contests on which one is the nicest, whatever. I recommend you don't use Google, but at some point, if you give up, the program is there. For me, it's not so important that you write it, but that you run it. Make sure you. It's very simple, but you have to do it. The first time there will be a problem. You forgot to work something.
So you will give us a...
Yes, they will be online tonight. Everybody has access to Moodle.
I don't actually. I'll mail
Email me.
Yeah,
You have the bidding today. So.
You have the.
yeah, but from chemistry from faculty.
So?
I have to do it manually.
You have to do something. Okay. Email me the ones that don't have Moodle, and I'll send it to you.